All right, so let's make a confidence interval. So really what this is going to boil down to is that one of the things that we can do here that we couldn't do before, it was we can actually take a sample and find the mean and the standard deviation from that sample. So because we didn't usually have a whole population, and if we did, we wouldn't have to do all this work. So one of the first things we're going to do is we're actually going to calculate what our sample mean and sample standard deviation are. We need to find a t-score, so we need to find degrees of freedom and the t-score. We need to find a standard error. Our standard error now is going to be s divided by the square root of n, meaning my margin of error is going to be the t-score times standard error, and this is going to be my confidence interval. So an easier way to think about this is that when sigma is known, that confidence interval was just x bar plus or minus the critical value that was a z, and then we had sigma divided by the square root of n. Well, oops. When sigma is unknown, what's going to happen is that we don't have z-scores anymore, so z-scores become t-scores. We don't have sigma anymore, but we do have sample standard deviation, so sigma becomes s. So the formula just really hasn't changed much. The only thing that's changed is that instead of having z, I have t. And instead of having sigma, I just have s. So not a lot has changed here. Okay. So I'm trying to get this information that we're going to need here soon up. So we're going to do a confidence interval. So I'm going to do this all in TI-84 because it'll be quicker just to do it all in one spot. So food chemists analyze the calorie content for a popular type of chocolate cookie. The following are the number of calories in a sample of 8 cookies. So as you see, we have 8 cookies, some 113, 111, 120, so kind of all over the place, but not too spread out. We want to find a 98% level of confidence for the mean number of calories in this type of cookie. Okay, so if you can, grab this data here quick, because we're going to take you over to a TI-84. So the information that we were given is we were given a list of data. So we were told that we have cookies, and these are the calorie counts of the cookies. So what we have here is a sample of 8 cookies. So we want a 98% level of confidence. And we do not know sigma, so we need to find a t-score. So remember, 98% is taken out of the center here. So that alpha would be 0.02 or 2%, and half of alpha would be 0.01. So the area in my tails is 0.01, and we're only interested in this tail. So we are looking for t, remember, because we don't know sigma, we're looking for t of 0.01. But we also need degrees of freedom. And my degrees of freedom are going to be those 8 cookies minus 1. So it's just going to be 7. So t 0.01 for 7 degrees of freedom. There we go. We're going to go to second bars. We're going to go number 4. So my inverting the t distribution. We're going to put in my area in the right tail. So 1% or 0.01. And we have 7 degrees of freedom. And what we get here is, if I round this out, I'm going to round it out here just so we can get a nicer number. That's going to be negative 2.998 is going to be my t-score. We don't usually round up 3, but we'll just do it in this case. So what we also need, if I want to figure out a confidence interval, is I have a sample. I need to know what is the mean of the sample and what is the standard deviation of the sample. So if you remember, the way to do that is we go to list, we go to edit, and we just put our data into our list. So just this data up here, 120, 118, 116. Okay, so I got 8 points. Then I'm going to go to second. Oops, sorry, we're not going to go to second. Then I'm going to go to stats again, and I go to calculate one var statistics. List 1, it should be L1. Our list should be list 1. And we see here, my mean, we round it, is 115.4. And if I get my sample standard deviation, this is the sample, that is going to be 2.83. I don't really have any rules for rounding right now. I'm just kind of rounding. Let's be fair here. We round out 3 here, so let's round the rest of this out to 3 places. So this would be, we'll say 375, and then we'll do 2.8. Instead of 3, we'll go 2, 5. We'll round out there. Like I said, just to make it a little more uniform, we'll round out to 3 decimal places everywhere. So that means I'll have to do 4 when I do my confidence interval. So for a 98% confidence interval, remember this is going to be X bar plus or minus my t-score for 0.01, because that's what's left there, because it's a 98% level confidence, divided by sigma divided by the square root of n. So my sample mean was 105.375 plus or minus my t of my t for 0.011% being left in the right tail. That's right, sorry. T should be positive. I forgot to convert it back to positive. So remember, that should always be positive, never negative. That was a mistake of mine. My S is 2.825, and then we divide this by the square root of the sample size, and that's going to be those 8 cookies. So one point, or 2.998 times 2.825 divided by square root of 8. That is going to give me 2.994. Technically, I should round out 1 more every time I do a new calculation. I should round out a little further. So we'll just round out 1 more here. So that is going to be my confidence interval. That's one form of it. The other one, 15.375 minus 2.9944. Well, second enter. If you make a mistake, you can do second enter and it'll bring it back, and you go second insert. There you go. Now I can put that missing number back in. All right. So now that looks a little more correct than 12. 112.3806 is less than mu, which is less than, so if I want the other side, second enter. So I can go back over to the minus, turn it to a plus, hit enter. 108.3694. So that is going to be my confidence interval. So that means for all the chocolate chip cookies, we expect that its mean is going to be somewhere in this range. Or not chocolate chip cookies, just chocolate cookies. Somewhere in there. And that range is pretty decent. So like I said, this is kind of actually how they estimate this kind of stuff. So if they were telling you what is the calorie count on something, probably they're going to do it with samples, and they're probably going to give you was really kind of like they figure out a confidence interval for it. And for you guys, for most people, they don't like to see a range of values. They just pick something in that range, and usually it's going to be like the average of the range, or not necessarily the average of the range, but it's going to be somewhere in there, like a rounded version of it. So that's usually how we figure this stuff out. So we don't know what it's going to actually be, so we have to calculate a confidence interval. And of course, they would do a lot more than 8 cookies, so they would have a much smaller confidence interval. It would be much more precise. All right, so this is another example. So a sample, so we know we got a sample. 123 people aged 18 to 22 reported the number of hours they spent on the internet in an average week. The sample mean, X bar, is 8.2 hours, and the sample standard deviation, S, is 9.84 hours. Oh, you don't usually see a standard deviation bigger than the mean. It happens, but you don't usually see it. We want to construct a 95% confidence interval for mu, the population mean. So we want 95% level of confidence. So 95% confidence level. So we want to make a guess at what the population mean for the number of hours spent on the internet for this age group. So probably because your standard deviation is bigger than your mean, this is actually a skewed population. But my sample size, N, is 123, and that is definitely bigger than 30. So my distribution of means is going to be normal. So we're pretty much good here. Basically, we're saying that whatever I do here is going to make sense because we have a normal distribution of means. Okay. So we're going to get rid of this part, and we're going to figure out the rest of this. So like I said, I'm going to do TI 84 just because it's a little easier to do it that way. So as a reminder, we are looking for 95%. So alpha is the 5% that's left over. Half of alpha is going to be the 2.5% left over. So that's what's in this tail here. So we are looking for T 0.025 for a degree of freedom of not 123, but 122. So one less than my mean here. So that T-score, we go to second vars for distribution. We go to number 4. My area is going to be in this tail is 0.025. And we have 122 degrees of freedom. So I like to use the calculator because 122 is not going to be on my table, but my calculator can find it for me. So remember, don't make a mistake I made last time. This is positive. So it's not negative 1.9795. We'll round it to the 98. This is going to be positive 1.98. So remember, this is a big sample, so this is going to be closer to that z-score we usually see for 95%. So 95% level of confidence or confidence interval. We're going to have X bar plus or minus the t-score times the sample standard deviation divided by the sample size, or square of the sample size. So we are going to have, our mean was 8.2 plus or minus S, which is, sorry, T plus or minus T, which is 1.98 times S, which is 9.84 divided by the square root of your sample size, and my sample size was 123. Usually the biggest mistake I see here is that you confuse your degrees of freedom and your sample size. And then when you start doing the confidence intervals, sometimes you accidentally put degrees of freedom in. So try to remember, this is supposed to be the sample size. So my margin of error is 1.98 times 9.84 divided by the square root of 123. So we are getting 820 plus or minus, and we'll just round it to the 1.75. So everything was 2 here, so we'll just round out one more. So 1.757. Sorry about that. There was an error and I kind of lost everything. So we have 8.2 minus 1.757. So this is my confidence interval, or you can say it's going to be 6.443, which is less than alpha, which is less than 9.975. So we think that somewhere in here is going to be the population. It's going to be the population mean, which is going to be hours, or average hours, of TV watched by people between, I think it was 18 to 22. So the sample was 8.2, but somewhere in this range, it could actually just be, it could be 9, it could be 6.6, but somewhere in there, we expect the actual population mean. All right, so one more example if you need it. So we have a potato chip company wants to evaluate the currency for its potato chip bag filling machine. Bags are labeled as containing 8 ounces of chips. A simple random sample of 12 bags finds a mean weight. So from the sample mean is going to be 8.12 ounces with a sample standard deviation of 0.1 ounces. So we're going to assume the weights are normally distributed. So if weights are approximately normally distributed, this is satisfied without having to look at anything else. It doesn't even matter what the sample size is. If the population of weights is normally distributed, we're good. So yes, that's verified. Next, we need to have a 99% level of confidence. So alpha is going to be 1 minus 0.99, which is going to be 0.01. Half of alpha is going to be 0.005. So when we're looking at the distribution, what's left in these tails, this is 0.99, Then we have 0.005 here, 0.005 here. So we're looking for T of 0.005. Okay. So I'm going to do this one with the table so we can see the table again. Also because this is on the table. Just a second. I think I accidentally closed my table out when I had everything had a meltdown there for a second ago. There's my table. So area in the tail. The area in the right tail is 0.005. My degrees of freedom, well, we have a sample size of 12, so my degrees of freedom are 11. And like I said, we do actually have 11 degrees of freedom on this table, so we can actually use the table and get a good estimate here. The table is good as long as we're not estimating. Like as long as 12 degrees of freedom are on here, as long as that correct area is on here, the table is just fine. But we need right here 0.005. So we're going to get that T of 0.005 is actually 3.055. So my confidence interval is going to be my sample mean of 2.18 plus or minus my t-score of 3.055 times my sample standard deviation of 0.1 divided by the square of the sample size, which is 12. So this is going to be 3.055 times 0.1 divided by the square root of 12. This is 8.12 plus or minus 0.0, we'll go 88. So like I said, just one extra decimal place. So the range that I expect the actual mean to be in is going to be 8.032. There we go. Since I made a little mistake there, to 8.208. So remember that what the bag says, it should be 8 ounces. So one of the things I could say here is that all bags are probably, or the average of all bags. Greater than the advertised 8 ounces. So this is once again kind of touching on what hypothesis testing is telling me. So the advertisement was it should be 8 ounces. My sample gets 8.12 with a standard deviation of 0.1 ounces. So once I construct this 99% confidence interval, so this is 99%, there is a 1% chance that I'm wrong. So the average of all bags is probably greater than 8%. There is a 1% chance I'm wrong. Or 1% chance it's not over 8 ounces. This doesn't mean that all bags are over 8 ounces. This means that if I took all the bags and I found the mean is over 8 ounces. So a large proportion of my bags actually contain more than 8 ounces of chip. More of them have 8 ounces than have less than 8 ounces. Or sorry, more have over 8 ounces than have less than 8 ounces. But this is kind of like what hypothesis testing is we have a claim, the company claims that they have 8 ounces in their, or they have an average of 8 ounces in a bag of chips. And we're saying, no, that is not wrong. The actual average is something greater than that. So we could go back and say, we deny your claim. We do not believe it is true.